In this goal, we'll be talking about significant figures, or sig figs, scientific notation, and precision and accuracy. All of these topics have to do with measurements and measuring accurately. So let's first look at significant figures, or sig figs. When we're making measurements, the last digit is always estimated. And this is a common mistake with students. They'll quickly read out what the ruler says or what the graduated cylinder says, and they forget to estimate one digit. Looking at ruler A and the object right there in between those two rulers, I see that I can for sure measure that there's a 4. So we'll say 4 centimeters. But if I were just to say 4 centimeters, I would be off by this quantity right here. So 4 only represents up to that point. I need to say that it's a little bit more. And so this is when I just eye it. So I'm estimating. My line there isn't that great, but I'm going to say maybe 4.8. Okay, looking at that first ruler. So let's look at the second ruler. So again, I can measure for sure that there's a 4. And because there are some additional lines, I can make one more measurement there. I know for sure that it's 5, 6, 7, 8. I can measure that. It is for sure 0.8. But now I have to estimate one digit. And so this is just your call, what your guess is. And I'm just going to say that's right in the middle. So looking at these two rulers, I have that I could measure to 2 digits in the first one and 3 digits in the second one. And so when we're talking about significant figures, we're talking about numbers that we have measured. And so for this first one, I have 2 sig figs, or 2 numbers that I measured. In the second one, I have 3 sig figs, or 3 numbers that I measured. So as far as what I was able to measure, I get a lot more from the second ruler than I do the first ruler. On the AP test, there will be 1 point given for the correct answer in the correct number of sig figs on the essay portion of the test. So it's only worth 1 point, but it's good practice throughout the year to just get used to expressing your answer in significant figures. So whatever answer comes out on your calculator, you don't write all the digits. Instead, you round to the appropriate amount of sig figs. Sig figs are all about expressing what was measured in the lab and maintaining that measurement throughout all your calculations. There's a list of sig figs down here at the bottom. This is also given to you in a reference sheet that's goldenrod colored, and you can find that on Canvas, or it should have been given to you in the classroom. Here's the rules. A lot of these rules have to do with the 0. Do we count the 0 or don't count the 0? Because placeholder zeros are not significant. So in other words, if you measured something to the 10,000th place, well, you're not going to count the 10th place, the 100th place, the 1000th place. So this first answer right here, or the first number right here, 0.00021, it has only 2 measured digits. So therefore only 2 sig figs. You don't count those zeros. Those were not measured. They just hold the place of the 10,000th digit. This next number, 7,000, that's just an approximation, and it only has 1 measured digit. It's an approximated digit. So there's only 1 sig fig. So looking at these rules, I'll just go through them really, really quickly. So the first rule is all non-zero numbers are always significant. So numbers 1 through 9, you always count them. The next one, all zeros between non-zero numbers are always significant. This is the sandwich rule. So if you have a number at the beginning and a number at the end, if there's a 0 in the middle, you always count it. Leading zeros are never significant. So again, those are just placeholders. Trailing zeros are significant only if there's a decimal place. So that first number there, 700 meters, that has 1 significant figure. But if I have a little dot after that last 0, then that means that they measured the ones place. So I would have 3 sig figs. So you need to really pay attention to where that decimal is. And then our last rules here, right here, my numbering got all screwed up here. So rule number 5, counted numbers and metric conversions have an infinite number of sig figs. So that means if you're counting something, then because you're not estimating a digit, then there's an infinite number of sig figs. So if I counted the number of people in the classroom and I got 32, I'm not going to estimate a portion of a person. So those counting numbers, they have infinite number of sig figs. And the same is true for our conversion numbers. So 10 centimeters is equal to 1 meter. Well, I could put 10.000 centimeter is equal to 1.0000 meters. It's infinite, the number of sig figs that are there. So whenever you look at sig figs, don't look at your conversion factors. Only look at usually the number you start with. So let's do some practice. A good rule that summarizes all those 5 sig fig rules is dot right, not left. Meaning if there's a decimal or a dot, you're going to start counting at the right and keep counting until you run into zeros at the end. And if there's not a decimal or a dot, you're going to start counting from the left and stop when you run into zeros. So if you'd like to pause the video and see if you can figure these out, please do so. Let's go through each of these examples. So I have a number at the beginning and a number at the end. So that means I do count all of these. This one has 5 sig figs. Number 2 down here. So there's a decimal. So dot right, not left. I'm going to start counting this way. So I'm going to go 1, 2, and then stop. 2 sig figs. So these numbers right here, these zeros are just placeholders. It means that just the hundredths place and the thousandths place was counted. Let's do the next one. So I have no decimal, so I'm going to start counting from the left, so this way. So 1, 2, 3, 4, and then I stop. 4 sig figs. So I don't count that last zero because it's just a placeholder. So that means they only measured to the tens place. The tens place was the estimated place. Number 2, again, a whole bunch of leading zeros, and there's a dot. I'm going to start counting from the right. 1, 2, there's 2 sig figs. Number 5, there's a dot. I'm going to start counting from the right. 1, 2, 3, 4. Stop when I get to zeros. Now for scientific notation, which we're going to talk about next, anything that's written here is significant. Otherwise, they wouldn't have written it. So this one has 3 sig figs. And you don't look at this portion. You just look at the numbers in front. Scientific notation is written so that the numbers express between 1 and 10. Let's look at rules with sig figs. So again, we measure in a laboratory, we want to maintain what we measured, even if we're doing calculations. So here I measured the mass of water, the mass of salt. When I add them together and I get my solution, how many sig figs do I do? When I just add them, I get this number, 150.5007. But how do I maintain the same degree of accuracy, or what is the least amount measured is what I'm trying to say. So the adding subtracting rule we don't use as much in AP Chem, but we do use it. So this is something to learn. And this one I call the how many places after the decimal rule. So what you're going to do is you're going to look to see how many places after the decimal. So this one has 1 place after the decimal, and this one has 3 places. So you're always going to go with the smallest. So not 3, I'm going to go with 1. So I'm going to go 1 place after the decimal, and I'm going to cut it off. So my answer for the solution is I have 150.5 grams of my solution. So again, use the fewest places after the decimal. So let's do some practice here. You can stop the tape and then come back and we'll see if you got the answer right. Okay, on this first one, first of all, just doing the math, you can type this into your calculator and that's what you're going to get. Okay, so again, you're going to look and see how many places past the decimal. So this one has 3 places and this one has 2. So I'm going to have 2, so I'm going to cut it off right there. Now this number right here, you can round. So if it is bigger than 5, then you're going to go up, and if it's lower than 5, then you'll just keep it the same. Not really round it down, just keep it the same. So this one's going to stay the same. So I do want to make sure that I write that 0 because it is measured. So again, only 2 places past the decimal. Let's do the next one. We're adding. So putting that into your calculator, just, hey, doing it right here. This is what I get. And again, I want to count places past the decimal. This one has 3. This one has 1. So I want to cut it out 1 place past the decimal. So I'll have 206.9 grams. So again, adding and subtracting, how many places past the decimal? So it's really the lowest or the smallest place. Let's look at the multiplication division rule. This one is used most in chemistry. On this one, you have to figure out how many sig figs each of the things you're multiplying or dividing have, and then your answer is going to be the one that is the least amount. So I have 3 different numbers here. So let's just go through and assign how many sig figs. This one has 2, this one has 3, and this one has 4. So what's the lowest amount? Is that 2. So I'm going to cut it off right here. Now look at this number. There's a 6. So that 6 is going to round that 7 up. So my answer is going to be 88, and meters times meters times meters is cubic meters. So this is when you would round. Now, if I was all done with my calculations, I would express it like this, but let's say I needed to take this 88 and do some more math with it. I would want to not round it yet. And so how you can represent that number is by writing it lower. So I'm going to carry an extra couple digits. So this is represented where it's kind of lower like that. It's telling me I only have 2 sig figs, and when I get all done, I'm going to round it. So it's just kind of a way to count how many sig figs you have, and then to maintain the number of sig figs in your answer as what you measured to begin with. Let's have you practice. So stop the video and practice, and then I'll give you the answer. Okay, this first number has 2 sig figs. The second number also has 2, and this last one has 4. So you're going to go with the lowest amount, which would be the 2. So I'm going to cut it off right here. 1, 2. That 0 is just a placeholder, and that will be my answer. And then I already talked about rounding errors. Carry a few extra sig figs during the problem if you need to. So on this one, if I need to carry it forward to do a math problem, in other words, if this wasn't my final answer, if I'm still doing something with this number, I would just carry a few extra sig figs. So this would tell me I have 2 sig figs, and actually that one, I think I'd round up to 2 because of that 5. Anyway, so I'll just carry a few extra sig figs, and at the end I would round. So this just avoids rounding errors, because if you take your answer from the first part of the problem and round it, and then the second part of the problem and round it, and the third part of the problem and round it, by the time you get to your answer, you might have an error. Here's just some more practice. Okay, the answers here on this first one, the answer is that number. We only have 2 sig figs as our smallest, and so I would fix this by writing in scientific notation 2.6 times 10 to the third, or you could just round it like this. So we do 2, 6, and then just have some placeholders. So either one of those would be correct for that first one. So it's a little bit different if you're on the left-hand side of the decimal, but that's how you do it. The answer to this, always do your parentheses first. That's your order of operations, and then 2.3. So only 2 sig figs because this first subtraction problem only gives you 2 sig figs, and then you multiply it, or excuse me, then you divide it. And this last one, we get 15.38, and this one has 1 place past the decimal, this one has 2. So I'm going to do only 1 place past the decimal, so I'll round it up. So there's my final answer. Let's look at scientific notation. We've kind of done a few problems with our sig figs with scientific notation. When you do write your scientific notation, you're only writing in sig figs. And it should have this pattern. So number, and then however many numbers there is, times 10 to some power. If you have a positive number, that means this is a big number. If you have a negative exponent number right there, then that means you have a small number. So let's put this in scientific notation. So looking at this, there's no decimals, so I'm going to start counting from here. So I have 1, 2, 3 sig figs. So again, the pattern is number, decimal, and then the rest of the numbers, and I have three sig figs. Then I'm going to put times 10, and then you need to figure out how many places you move that decimal. So even though the decimal is not written, it's assumed that it's right here, and I can count how many decimal places I moved it. 1, 2, 3, 4 places to get it in between the 5 and the 0. So it's going to be 5.09 times 10 to the 4th. Let's look at this one. This one has a decimal, so I'm going to start counting from this direction, and I have 1, 2, 3 sig figs. The rest are placeholders. So 7.09 is the pattern. And then I'm going to do times 10 to the, and then find where the decimal is and figure out how many places you move. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 to get between the 7 and the 0. And remember, this is small, so it needs to be negative. So to the negative 10th. So 6 times 10 to the negative 1 is how I'd represent that. I moved my decimal to the right and made the number bigger, so it should be a negative exponent. And let's do the next one. So I'm going to move the opposite direction. So 5.4 times 10 to the 1. So sometimes you see it like this. I think it's just easier to write 54, but there is 54 written in scientific notation. All instruments have a certain amount of inaccuracy, and that's because we're always estimating the last digit. And there's just human error when you're measuring things out. Most of the time in this class, we will use a graduated cylinder to measure all volume. We're not going to measure with a syringe. Burette would be the most accurate way that we could measure, and that's because we can get 2 places past the decimal. A pipette, some pipettes are marked. So if this was measured to 1 milliliter, and you wanted half, then you can measure to that 0.5 milliliter. When mixing up solutions, I use a volumetric flask. These are very specific for the final amount of volume that you have. So if I had a 1 liter volumetric flask, I could only measure to the 1 liter. So whatever final amount that you have, you want to make sure you use that volumetric flask. If I needed 250 milliliters, I would not use the 1 liter because there's no marks down below. There's only one mark, and it's the 1 liter mark. So I would have to use a 250 milliliter volumetric flask. So I have lots of these for mixing solutions for different volumes. Let's talk about accuracy versus precision. Accuracy refers to how close your measured value is to the real value. So if you were to use a burette to measure a liquid, you would get closer to what you're really dispensing versus the graduated cylinder. And the graduated cylinder would be better than a beaker because a beaker is not used for measuring anything. Even though it has some numbers on the beaker, we don't measure volume in it. That is just to help us know approximately what's in the beaker. Now, precision refers to how close your values are to each other. So just to give you an example, if we have a dartboard here. So if we throw 3 darts at the dartboard, if they all hit the bullseye, then we say that we have good accuracy. I'm just going to put A for accuracy. And because they all hit the bullseye and they're all close to each other, I also have good precision. Now let's look at this one. Didn't hit the bullseye, but the darts are close to each other. So I have good precision, but poor accuracy. And you could say good or bad. And let's look at this next one. This one's having a bad day. So poor accuracy and poor precision. So they're not close to each other and they didn't even hit the bullseye. So in science, we obviously want to get this first one. We want to have our measurements be accuracy, so close to what it's supposed to be. And we also want if we measure the same thing like 4 times, we want each of those measurements to be as close to each other as possible. If I have this center scenario where I have good precision, there might be something wrong with the balance that you'll have to just correct the balance and readjust it, maybe recalibrate it. Percent error describes how far you are away from the expected value, and percent yield tells how much you have in comparison to how much you would have had, like what your math says. So that's percent yield. And in AP chemistry, we use both of these, but use the second one most likely. So percent yield.